session of inverse modeling with prior uncertainty, we'll cover sequential importance resampling. What's the motivation for this method? Consider here the Hurricane Sandy, which was devastating for the area, the New York area. And so in a hurricane, we often see predictions made out of paths. So here on the left-hand side, we see two diverging forecasts. One is the red path forecast, and another is the blue path forecast. And then here the black is the ultimate forecast. So what we have here is a problem of uncertainty. Obviously, is that if the hurricane is at this particular location, then there are many paths we can take. You see that the red model can go both ways. The blue model only indicates going that way. But of course, this uncertainty is not just one instance in time. When a hurricane moves and moves, say, up, then we have to update the uncertainty of the path moving forward. And so this continuous updating with information needs to be addressed. In the previous sessions, we only talked about sort of a one-time update of uncertainty. We have a prior distribution, we have some data we update, and we get a posterior distribution. So what if we have time-varying data, where there's sort of a data stream that comes in over time? And this is sort of explained in a similar sense here, is that we start from some initial prior uncertainty, of a point with some uncertainty. We make a forecast, and we have multiple of these paths, which is the same as in the hurricane example. Then we get a new location of the hurricane, which is, say, over here, and then we have to update the uncertainty. That means that this is now the prior distribution of the prediction. This is observation, and we need to create a new path forward. There are many names to this kind of procedures: data assimilation, bootstrap filter, particle filter, ensemble common filter, sequential importance resampling. But essentially, all these are basically applications of Bayes' rule, but now including time-varying data. So there are many examples of this in the subsurface. For example, geophysical monitoring, which is then called 4D geophysics. Classical examples would be time-lapse ERT data, which we've covered in the previous lectures. Also 4D seismic data. When we have production data, say in oil and gas reservoir, or continuous stream monitoring in hydrology, then we also have this kind of time-varying data. So we just need to extend now our notation a little bit. So now instead of having just a single model at some time, a model at some time instance M0 with a prior distribution and a prior forecast, now we'll have, we can build many models and their distributions at various stages in time. And so this is the notation that is being used here. This is time 1, time t minus 1 till time t. And so we have the data variable, which is simply applying the forward model on each model variable. And then we have applying the forward model for the prediction on that, we get that. And then, of course, we also have our observations. The obvious solution to this is just to repeat the Monte Carlo exercises that we've seen in the previous lectures, each individual time step. But of course, that would be very efficient. It would mean redoing the entire exercise every single time step. And if data becomes available very quickly, then this idea would not work very practically, simply because the amount of computation and modeling time would exceed the data assimilation of the data that's available. So a first assumption that we make is to make a Markovian assumption, where we succeed that an unobserved signal is conditionally independent on previous states, and only depends on the previous state. So it's a simple idea again, where we say that the weather tomorrow is only dependent or can be modeled perfectly from the weather today. We don't need to know the weather yesterday. There's this conditional independence that's being created. So in terms of probabilistically, this is then stating that we have a prior distribution. And then we state that our next model is only dependent on our, given the previous model, then there's a conditional independence here. So given the previous model, these are no longer providing any additional information on MT. And so we write this assumption, and the same for, of course, the data assumption. So the data variable, given the model, I don't need to know all these models to model this distribution. I only need the previous model in order to model this likelihood function. So the aim here, therefore, is to come up with a recursive kind of, in the sequential, which is called sequential Monte Carlo, where we have a recursive application of uncertainty quantification. So the aim, therefore, is to estimate recursively this following distribution. So this is the distribution of all the models in all time, given the data that we have. So this is the full posterior distribution of all models. If we integrate out all the models except the model T, so we calculate the marginal distribution, then we get this marginal distribution. And of course, distribution that we are very interested in, because that's the update of the uncertainty on our state, MT. We also would be interested in any kind of expectations. So here we have some kind of forecast of interest. That could be, for example, something happening in the future oil production, and what have you not. So this would be then an expectation. You see that this is written as an expectation of the function h. And then also, like here, we can calculate the marginal distribution by only focusing on the prediction made by the current model and this current marginal posterior distribution. So you could also go and do direct forecasting, which is essentially saying that we're using the model as a hidden variable, and we basically look only at uncertainty on the forecast given the data, and we sort of don't bother too much with the model itself. So to solve the previous problem, means obtaining this posterior distribution, we can write that using Bayes' rule in this following sense. So we have the likelihood distribution, we have the prior distribution, and the normalization constant. So now we can write the same, but going to the next step. And so with some calculation, you can show that the next posterior distribution, which is then the posterior distribution of this term, as you know that you have a t plus 1, as opposed to here t, we have additional data t plus 1, is equal to this distribution times this update factor. And so this update factor, we see a likelihood function appearing. We see this conditional distribution of the next model given the previous model appearing, and also for the data. So the way this is then solved is that we, in terms of marginal then, so I'm only interested, say, in what happens here. So what's the updated uncertainty of the model given the data, is that first we take our current posterior distribution and we forecast. So we run basically many forecasts. That's what you saw in the hurricane example. We run many forecasts, and then we get new data at some time t later, and then we update that uncertainty in this fashion here. So this DMT has to be removed here in this case. So that's all very theoretical, because it doesn't really say here. It doesn't really say here how to calculate all these integrals and these distributions. And so what people then, of course, do is make assumptions. Typically, for example, on some ensemble filter, we would typically make Gaussian assumptions, and then also some assumptions on the four models being used. So this is what sort of visually stated in the previous slide. So imagine our hurricane is apparently at this position here. So we make a forecast. That's our predict step, which gives us then this distribution, which is the green distribution here. Then we have an observation, and so we have now a prior distribution observation. We apply Bayes' rule, and we update the distribution as follows. So how do we now solve this practically? So to do that, we'll talk about a couple of issues. First of all, is Monte Carlo integration, which will be useful in understanding how all these integrals are calculated. Then there will be something about importance sampling. So we have to calculate these integrals very efficiently. We don't want to waste a lot of samples or models where we don't need them. And then, of course, we need to come into a sequential application of importance sampling, because we have time-varying data, and that will be called sequential importance resampling. I think the sequential importance resampling is probably one of the most general methods that you can apply in this kind of data simulation context. So let's talk a little about Monte Carlo integration. As a matter of fact, Monte Carlo was often used initially to solve integrals. And solving integrals in high-dimensional spaces, when that dimension becomes more than 5 or 6, becomes very problematic. We saw that the space becomes very empty very rapidly, and so doing it by discretization is very difficult. So another way to solve it is by Monte Carlo. So instead of doing a regular sort of cutting up of the space in many cubes or squares and calculating the integral numerically, we just do Monte Carlo simulation over the domain and then calculate this integral. And the way you could see this is as follows, is that if, for example, this f of x is xg of x, and g of x is a positive function whose integral is unity, then what I basically have is an expectation. So in order to calculate an expectation, the way we do that is through to estimate the expectation, is the way we do that is through Monte Carlo. We just generate many samples, and we calculate the arithmetic mean of x, and then we get an approximation of the expectation. And of course, the more samples we take, the better our approximation will be. And so there will be gradually, as we get more samples, there will be reduction of variance. It means accuracy, increase in accuracy. So, and here's this a little bit more formally. So we'd like to calculate this expected value, which is defined through this integral. So, and now we turn the sort of problem around and say, how do I calculate this integral? Well, this integral is calculated through Monte Carlo by sampling from this distribution f of x. And then once we have many samples, we calculate simply the arithmetic mean of h of xl. So that provides us then an estimate of this quantity here. But of course, in UQ, we're not just interested in calculating mean values. We can also use the same idea to calculate CDFs or empirical CDFs. And that is, of course, a common application as well, as I want an empirical CDF of h of xl. I write it here simply as this formulation with the step function in there. So how accurate is this now? It's obviously that the more samples I get, the more accurate it becomes. So there are of course, some analytical solutions to this problem. If you have Gaussian and independent samples, if your distribution is Gaussian, and you draw independent samples, then we know the variance of that estimator is simply the population variance divided by the number of samples that I have. So that would be same apply to the prediction that I would like to make. So that I have, of course, an uncertainty of a variance, say a prior variance of this prediction that I'd like to make, and that gives us this equation. So this approximation shows that, of course, that the more varying your population is, the more samples you need, and the more samples you get, better your approximation becomes. If you do just Monte Carlo, naive Monte Carlo, then you're sort of saying if I have two variables, x1 and x2 here, so this x is now bivariate, then I'm exploring the space in this kind of sense. But you see, this is not a necessarily efficient way of exploring the space, because we get a lot of these cluster samples that sort of we really don't need. And so one idea is then to say, can we do better than this naive Monte Carlo? And so can we improve on this sort of basic formulation of the accuracy? And those methods are called variance reduction methods. So in variance reduction, we try to achieve that. And one way to achieve that is to, for example, do stratified sampling. To do stratified sampling, we cut our space up into pieces. For example, our previous two-dimensional space is now cut into pieces. And we sample a number. If you do uniform sampling, we sample a number of samples within each of those pieces. We can also do this in terms of concentric circles. The problem with this is that this, again, runs into the dimensionality problem that we actually tried to avoid. Remember that in solving the integral, we ran into problems in very high dimensional spaces because we had to cut up our regions into many tiny hypercubes. And so if you can imagine doing this in higher and higher dimensions, you need an exponentially more subdivisions of your sample space. So this idea really only works in low dimension. Solution to that, which is quite neat, is called Latin hypercube sampling. So in hypercube sampling, we're not going to put many samples in each square. We're just going to put one sample in each row and each column. So here we see in this row column, there's one sample. In this row and this column, there's one sample, etc. So in that case, you can create many of these Latin hypercubes by going through all the combinations that are possible for this Latin hypercube sampling. Another method for variance reduction is called importance sampling, and this is a method where we focus on, since I believe that has the most relevant to uncertainty quantification in the general case. So here's a sort of an idea of where this can be applied. So suppose that you'd like to estimate the probability of exceeding a certain threshold. And so if you would like to, if you don't going to do Monte Carlo, you would be drawing from that from your distribution, and we just count how many times you get over that threshold, and that frequency will then be an estimate of your quantity of interest. But you can understand if this threshold is very high, then I need a lot of samples to do that. As a matter of fact, if my actual distribution is a standard normal distribution, and I draw 1,000 samples or 100,000 samples from it, you see, by the 1,000 samples I don't even get there. I don't get any exceedances. Then with even 100,000 samples, then my estimate of the probability of being above threshold 4 is 3.5 10 to minus 5, while the actual one that I calculate from the normal distribution is 3.167. So we see that there's a substantial error here that occurs despite the fact that I have 100,000 samples. So as you notice that this doesn't work really very well if you're going to do naive Monte Carlo. So what I'd like to have, and this is the idea of importance sample, is I'd like to have more samples in this area of interest. I don't care about samples that are happening over here, so why should I draw them in the first place? So the way then to proceed could be that you place this green distribution over the area of interest, and you sample from this green distribution. The problem, of course, is sampling from this green distribution is that you're not sampling from the actual distribution. And so then what we need to do is to correct the sampling idea by accounting for this difference. And so the way that is done, as you'll see, is that we'll keep the samples from the green distribution, but we weigh them with different probabilities. And so, for example, here it makes a lot of sense that you're oversampling in this area and you're undersampling in this area, so you want to weigh the samples not with equal weight, but with weights that are related to the difference between the green distribution and the blue distribution. So this is what is said here. So if I'd like to calculate quantity of interest, then I have here h of x times f of x, but now I introduce a new distribution, that green distribution, which is that distribution q here. And so then I notice that I can sample from the green distribution, but I have a ratio here now, which is how I should correct these samples. So this is expressed in the Monte Carlo version of this. So if I do Monte Carlo, I generate many samples from the green distribution, this q here, and then I correct them with this weight. So now I can calculate this weight if I have an expression for my blue distribution and my green distribution. I can calculate these weights, and I get these weights over here. And so I calculate my quantity of interest in this particular fashion. So if you apply that to a simple case, and we put a new distribution, Q, the green distribution now centered around an area of interest, which was 4, with some variance, then I find with very few samples, I think 1,000 samples here, we find that the estimate provided by the importance sampling is pretty much the same as provided by the actual distribution. Come to the sequential application of importance sampling. Say we're in importance sampling and we get data in time. And so the idea here would be then, of course, to steer your sampling in the areas where you have the data. But of course, you don't want to sample from anything else in the prior distribution, otherwise you're not applying Bayes' rule correctly. And so we have to therefore consider the difference between the distribution I sample from and the prior distribution. So if I take my previous, in the previous slide, this equation for estimating some quantity of interest using importance sampling, then the only thing I need to now replace here is this expectations, which now is replaced by that. This is now the current distribution of my models. This is the target distribution, will be an auto distribution that I sample from. And so my X is now the various models. And so what I write is then this equation of importance sampling in that fashion. So you notice here that I need to be able then to calculate the ratio between this prior distribution or the current posterior distribution, let's say, or the current updated distribution and this proposal distribution. And so this is also called particle filtering because what we're doing is we're keeping these models into play, and what we're doing, instead of creating many more models, what we're doing is we're constantly reweighing the models using some weights. That is a ratio between the distribution I'd like to sample from and the proposal distribution, the targeting distribution. Okay, if that sounds all very complicated, let's do a case study. I think that will clarify a lot of the material. So here we have the Libya case. We've shown that before. It's an oil reservoir. We have many types of uncertainties. And we like to predict future production in this reservoir. So, and we may, of course, get, as we produce the reservoir, we get new production data, and so we need to constantly update our uncertainties regarding this future production. So we can apply the direct forecasting. That's what we showed in the previous slide set, where we're going to build a direct relationship between H and D. So here we're going to use importance sampling in terms of essentially the H and the D, and not necessarily of M itself. Simply because M is very complex, and so it becomes very difficult to calculate these very high-dimensional integrals when we're dealing with a very high-dimensional model. It will become much more simpler when we're dealing with the data and the forecast here, because the data and the forecast here are just time series. So here's our time series. So we have our current state. We are today at 3,500 days of production. And so we have, this is our past, and this is our, from our prior. And so this is our actual data. And so what we now need to do is, imagine you started at 0 and you come here, so we need to do our first update step. That means is reduce uncertainty on this forecast. And that's what forecasting did. So remember our little slide is the way it's done is we take the data in the previous slide, we do dimension reduction, we run canonical correlation analysis, we try to find then a linear relationship in canonical space, define there the Gaussian distribution as a relationship between the prediction variables in canonical space and the observed data in canonical space. We estimate this distribution and we sample from it, and then we reconstruct the samples. So here is, for example, the result of the first canonical component of the data and the first canonical component of the prediction. And we notice there's a nice linear relationship, and here's our observation. So this allows them to reduce uncertainty on our canonical variable for H, and we can do that for all of the canonical variable of H. Then we can sample from the posterior distribution. This is simply a Gaussian distribution. In this case, we can estimate that Gaussian distribution based on all this empirical information, and we can do an update. So that's what we see here. Once we have that, we do an update. We get a reduced uncertainty on our future prediction as compared to that. So you imagine this is the hurricane. The hurricane is longer the gray paths. It's now the blue paths. Okay, now we get more data, and we also get a different prediction problem. Say we are at 4,500 days, and we'd like to drill a new well. We'd like to understand the future prediction by drilling that new well. And so we are at 3,500 days. We had made our forecast. So now we're at 4,500 days. We need to make a new forecast. And now, of course, we have more observations. So we actually have all the observations from 3,500 days up to now also 4,500 days. Instead of just redoing the whole exercise, which would be time consuming, we'd like to leverage the exercise or the uncertainty reductions that we had done at 3,500 days. So what that means is that if I represent all this information again into this lower dimensional space, then what I get here is that my data previously was over here, so now we have new data, so it's shifted over here. So I'd like to have the samples over there. So this is also the old distribution that I had. So now of that generated from my prior distribution of M. So I'd like to generate more samples over here. I don't want to keep sampling from that prior distribution. That would be a waste of time because I know that I'm not over here, I'm over there. So this is sort of the idea is that I'd like to sample from this distribution by some targeting, but in that sampling, I may not actually draw from the actual posterior distribution, but some approximation. And so if I make any approximation, then I'd like to calculate some weights that correct for that. So how do I do that? What is my proposal distribution? Well, my proposal distribution would be sampling more models that are more targeted. And the way to do that is, of course, to reduce uncertainty on the models themselves. So here, we notice, for example, that in the data space, so this is the first principal component of the data, the second principal component of the data, so this is the data up to 4,500 days, we have now essentially the oil-water contact as a color here, and here's my actual observation. So it's very clear that our actual observation is more in agreement with high water oil-water contact and not with low ones. So if I do a simple application of Bayes' rule in this graph, then I get this updated distribution, which will be my new distribution. And so now I can sample from this blue distribution. And I can do that for all the other parameters, including potentially spatial parameters. And so doing that helps me with target distribution, targeting the sampling more. However, we have to understand that this is an approximation, because the actual updated distribution is the joint distribution of all of the model variables given the observation. What we're doing here is what we did in the previous slide is just have individual univariate conditional distributions. So what we're doing is we're writing this joint distribution as a product of these conditional distributions. And so this is now the definition of our target distribution. So what we're doing is we're sampling new models from this distribution. We're calculating a forecast and a data prediction. And so then what we need to do is, if we do any updating, is we need to weigh those samples that I just drawn, so the samples here, according to this ratio. The problem is that I don't know this ratio because I don't know the actual real distribution. I only know the proposal distribution. So the way to see that, or the way to avoid that, is to not focus on the models, but again to focus on the forecasts. Instead, what we're going to do is we're going to go the samples generated from this, our previous distribution, and calculate basically the direct forecasting step on those samples, calculate the direct forecasting step with our proposal distribution, and then weigh them accordingly. So, and that is what is shown here. So here we have our prior distribution was the gray distribution. We have our target distribution, but our target distribution has to be reweighed, and then reweighing is with respect to this this prediction variable. So the prediction step, you notice that here's the mean of the prediction step, that these samples are obviously overweight and these samples need to create higher weight, these lower weight, because these are samples in the tail of the distribution. And so that's how we do this overweighing. We're creating too many samples over here and there, so we underweigh those relative to the actual distribution. So here we see the same, but now in terms of coloring with the same weight. So here have the high weighted samples, and here are the low weighted samples. So if we keep repeating this, we may run into a problem, and that means that we keep sampling fewer and fewer models that get higher and higher weight. So this is also called sample degeneracy. So there's an increased skewness in this weight. So it means after a few iterations, there's only really few samples that are left that have big weight. So the idea of resampling, so the sequential importance, the sequential repetition of importance sampling, would then need to include a resampling step, and this is also called bootstrap filtering. So the way the resampling works is that we first normalize the computed weights, and then we do simply bootstrap based on this empirical distribution created with these normalized weights. And since each weight is associated with a model, in this bootstrap, we're essentially resampling models according to this distribution. And so what this will do is this will tend to remove the low weight sample and increase the high weight samples in our population, in our pool. So if we do that, then we get this this bootstrap here. We get this bootstrap bootstrap samples, which are now resampled, and we get more, as you notice, more of the high weight and the low weight samples have been removed. So once we have that, we can then update the quantiles and responses for the posterior distribution, and we see here that we get an updated forecast using the sequential importance resampling. And so when we get more information, we just can repeat doing this step. So that means here collecting more data. That means maybe again we change the location of D. We do the same step. We create new updated uncertainty in our model parameters, and then we sample from those, and then we reweight them and we resample them, and we get an update again of our posterior distribution. So sequential importance resampling in recap, it's a lot of dense information here in a few slides, but I hope you got an appreciation of the power of these kind of ideas and the idea of continuous data assimilation. So data assimilation is a big word, but it it has many forms, and essentially they're all forms of Bayes' rule. And I do believe that sequential importance resampling honors Bayes' rule to the largest extent. In that sense, sequential importance resampling is sequential because it's sequential Monte Carlo. It relies on importance sampling, targeting the sampling of the distribution in a certain area, and resampling is correcting for bias and avoiding sample degeneracy.